We now have two talks before the lunch break, and it's my great pleasure to introduce Sophie Langer from the TU Darmstadt, who is working on various aspects of statistical theory of deep neural networks. And today she will speak to us on, is sparsity really the answer? Sophie, please, the screen is yours.
Thank you for the introduction, and hey everybody, welcome to my talk. Today I'm going to talk about the question, is sparsity really the answer? And this talk is based on joint work with Michael Kohler and Ulrich Reif. And I would like to start with a short motivation of the topic. I think all of you know that deep learning have achieved impressive results in various applications like speech and pattern recognition or autonomous driving. But unfortunately, from a theoretical perspective, we do not really understand why this method is so successful in practical applications. And yeah, the main problem is that describing the procedure of these deep neural networks at hand is a highly complex task. First of all, we have to think about the right network architecture, including the number of hidden layers and number of neurons per layer. Then we have to choose the right activation function. And finally, one has also to describe the optimization algorithm. And while the empirical results of deep learning are further enhanced, like in the context of reinforcement learning by using convolutional neural networks, the theory is lacking behind with very isolated results in simplified settings. And we can roughly divide the theory right now in three parts, namely the approximation, the generalization, and the optimization. In approximation, we think about which function classes can be approximated by neural networks. In generalization, we try to answer questions about why do neural networks generalize well on unknown new data. And in optimization, we consider the energy landscape of the networks. And my today's talk is in this intersection of these two circles here. So I assume that the optimization works optimal, yeah, and we only consider these two things of the networks. Okay, and before we get started, I need to define some components of the neural network. So today we will consider simple vanilla feed-forward neural networks, and we choose as the activation function the ReLU activation function, so the rectifier linear unit, which is the maximum of x and 0. And furthermore, we have to choose a network architecture, and this architecture depends on two parameters, a positive integer L, which denotes the number of hidden layers, and a width vector K, which denotes the number of neurons in the first second till the Lth hidden layer. And I think all of you are familiar with the definition of neural networks, so I skip the formal mathematical definition. And yeah, what we want to do with the neural networks now is that we want to study the statistical performance of these fully connected deep neural networks. And the most convenient way to do this is to analyze neural networks in the context of nonparametric regression. But what is nonparametric regression? So therefore we have to consider the following prediction problem. We have given an RD times R valued random vector x, y, and our aim is to find a functional relation between x and y. So we're trying to predict y by a function f star of x, and f star goes from RD to R. In particular, we are interested in a function f star such that the so-called L2 risk here is minimal. And one can really compute this minimum and can show that this minimum holds for the function m of x, which is equal to the expectation of y given x equal to x. And that's why one calls m the so-called regression function. So now we would be finished if we would know the distribution of x and y. Unfortunately, this is not the case in most of the practical applications. And the only thing we have given is a set of n observations, dn, which consists of pairs x1, y1 to xn, yn, which have the same distribution as x and yn, which are independent. So what we want to do is that we want to reconstruct our function m by an estimator mn, which uses these observations dn. And yeah, we want to construct the estimator in a way such that the so-called L2 error is small. And one possible estimator is the so-called neural network regression estimator. And this estimator is based on a class of neural networks. We abbreviate this class by f of L and R. So we consider all fully connected neural networks with L hidden layers, R neurons per layer in the ReLU activation function. In the setting, we have to choose the number of layers and the number of neurons per layer in dependence on the sample size. So we say L is equal to Ln and R is equal to Rn. And then we can define a corresponding neural network least squares regression estimator by using the principle of least squares. So we choose the function out of the function class f of Ln and Rn, which minimizes the least squares loss. And for our theoretical analysis, we need to truncate this estimator on some level constant times log n, which means that our final estimator mn is equal to mn tilde as long as its absolute value is smaller or equal than constant times log n, and otherwise we just cut this value on this level constant times log n. And now we are interested in analyzing the expected L2 error of this estimator. In particular, we're trying to find a bound which depends on n, and this dependence on n finally gives us the rate of convergence of our estimator. But before we do this, we have to think about for what kind of regression functions do we want to perform our estimator well. And a classical idea would be to assume that our regression function fulfills some sort of smoothness. So sometimes we say some PC smoothness, which is a higher order Hölder smoothness. But for simplicity, you can just think about regression functions which are p times continuously differentiable. And for this rate of for this class of regression function, Stone could show in 1982 an optimal rate of convergence of n to the minus 2p over 2p plus d. The problem of this rate is that in case that p is small compared to d, this rate gets rather slow. And this is known as the curse of dimensionality. So if the class of p times continuously differentiable functions would be the right class which we should consider in analyzing our neural network estimator, we could not expect better rates as this here. And this would not really give us an answer why neural networks perform well in high dimensional spaces. So the aim is to find a proper structural assumptions on our regression function m, which makes us believe that we can also get better rates in high dimensional spaces and which are also realistic in practical applications. And one possible way would be to assume that our regression function has some sort of a hierarchical structure. Therefore, I've brought the following example for image processing. So if we consider the following handwritten digit and ask a computer to tell us which handwritten digit is on the picture, then we could think about how can the computer solve this task. So first of all, he could just detect edges by combining neighboring pixels. By combining these edges, he could see local patterns, and by combining these local patterns, he could finally, see the object. So in this heuristic, you already see this hierarchical structure I was talking about, and you also see that for the subtasks here, we do not really need all of the input components. So for example, when we consider these edges here, we only need the upper left corner of our image and not the input of the whole image. And this leads to the following definition of a so-called hierarchical composition model, which has a recursive definition. So we say that M satisfies a hierarchical composition model of some level 0 if M of x is equal to some component of x. And then we can say, okay, M has a hierarchical composition model of some level L plus 1 if we use k values of the previous level, so k functions f1 to fk, which are a hierarchical composition model of some level L, and combine them in a functional way by applying a function g. Okay. And we also need some smoothness assumptions on this model, and we say that our hierarchical composition model satisfies a smoothness and order constraint p if p is a subset of 1 infinity times n, and if all functions g have input dimension k and are p times continuously differentiable for some tuple pk, which is in P. And for the theoretical analysis, we need two more further assumptions. On the one hand, we assume that all functions g are Lipschitz continuous in our definition, and we have the standard assumptions on the distribution, y squared is sub-Gaussian, and the support of x is bounded. And before I show you my result, I want to show you two results from the literature. And the first one goes back to Johannes Schmidt-Hieber, who also considered neural network regression estimators. And he, in his setting, he chose a number of hidden layers of order log n, a number of neurons per layer of order n to the c, where c is larger or equal to 1, and a number of active neurons of this size here. And then he could show for a corresponding neural network estimator that this estimator achieves a rate of convergence of maximum of n to the minus 2p over 2p plus k. So what you see here is we get a rate of convergence which does not depend on our input dimension, but only on the dimension of the hierarchical composition model. In his setting, he also had this term number of active neurons. And this means that not all neurons in consecutive layers are fully connected to each other. So we only have a restricted number of connections in the whole network. A result of a similar flavor was shown by Bauer and Kohler in 2019. They considered a slightly more specific class of regression function, namely the generalized hierarchical interaction models, where where D alternates between the smoothness and dimension D star and P, and K and infinity. So in every second level of this model, G is chosen to be a sum, which has smoothness infinity and has K components. And they also considered a sparsely connected neural network estimator, but this time with a smooth activation function, in particular a sigmoidal activation function. And they showed a rate of convergence of the estimator of n to the minus 2p over 2p plus d star. So you see this time again, this rate does not depend on the input dimension, but only on this dimension d star of the hierarchical model. So what show us these existing results? We see sparsely connected neural network regression estimators are able to circumvent the curse of dimensionality if we impose further structural assumptions on our regression function. Furthermore, the findings lead to the conjecture that in order to achieve these good rate of convergence results, one should use neural networks which are not fully connected. And as my following result shows, this is not true. So when we take simple fully connected neural networks with a number of hidden layers of order maximum of n to the k over 2 times 2p plus k, and the number of neurons to be a large enough constant, or a number of hidden layers of logarithmic size, and a number of neurons of order maximum of n to the k over 2 times 2p plus k, then we can bound the expected L2 error by constant times log n to the 5 times maximum of n to the minus 2p over 2p plus k. So you see here, this rate of convergence is the same as we had in the result of Schmidt-Hieber, but this time we do not need this sparsity constraint in the setting. So summarizing, we see deep neural networks are indeed able to circumvent the curse of dimensionality if we impose further structural assumptions on the regression function, and that sparsity is not necessary to derive these good rate of convergence results. Another thing which we had considered is, so most of the results in analyzing nonparametric regression estimators in neural networks focus on the structure of the underlying regression function and less explore the geometric properties of the data. But it is indeed interesting to also consider these properties of the input data, as in many high-dimensional problems, they can treat it in a much lower dimension. For example, in a high-dimensional vector, we have many redundant information which not really influence the output. And that is why we have asked ourselves, are deep neural networks also able to exploit the structure of the input data? And therefore, we have formulated the following assumption. We have said, okay, our X is now concentrated on some D-star dimensional Lipschitz manifold. And this is how we define this D-star dimensional Lipschitz manifold. First of all, we said, okay, our M is a subset of Rd, which is compact, and D-star is out of the set 1 to D. Then we define an open covering of M by sets U1 to UR, which are also subsets of Rd, which are open and which satisfy that M is a subset of the union of the UL. Furthermore, we need the definition of B-Lipschitz functions, and we say psi1 to psi-r, which go from 0, 1 to D-star to Rd, are B-Lipschitz functions if we have some constants C psi1, C psi2, such that this condition here holds. So we have this standard Lipschitz condition and then the condition in the other way around. Okay, and then we can define a D-star dimensional Lipschitz manifold if there exist B-Lipschitz functions psi-I and an open covering U1 to UR of M such that psi-L of 0, 1 to the D-star are equal to the intersection of M and UL for all of the L in 1 to R. And under this definition on our input data, we could show that if we choose a number of hidden layers of order log n and a number of neurons of order n to the D star over 2 times 2p plus D star, we can bound our expected L2 error of the corresponding least squares regression estimator by constant times log n to the 6 times maximum of n to the minus 2p over 2p plus D star. So again, we see the rate of convergence does not depend on the input dimension, but only on the dimension of our manifold. So indeed, the neural network estimator is able to exploit the structure of the input data. And as we have some time left, I want to show you the main trick of the proofs. So the first thing is a standard bound of empirical process theory. So what we use is that we can decompose our expected L2 error in 2 terms. The first term here, which depends on the covering number of our function class, kind of measures the complexity of the function class. And in the second term, we have the approximation power of the networks. And here we see, okay, we need to balance these 2 consecutive errors. So like we have seen in the talk before, so if we enlarge the complexity, then we get a better approximation power. But yeah, we have to find a good balance between these 2 terms, because otherwise we have here too big an error which is too big. And for the first term, we have used the result of Peter Bartlett and co-authors, which derived a bound on the VC dimension of neural networks in terms of the overall number of parameters. And as we can bound the covering number by the VC dimension, we can finally use this result. And for the approximation power, we have used a 2-step approximation where we have partitioned our space in a finite set of a coarse and a fine grid. And then we have approximated Taylor polynomials on each of these cubed by deep neural networks. And then by combining these 2 things, we can finally show the bounds. Okay, so let me summarize what we have learned today. So we have seen neural networks are able to circumvent the curse of dimensionality if we impose on the one hand structural assumptions on our regression function, like in our case these hierarchical assumptions, or if we impose some geometric properties on the input components. In this case we had this manifold assumption. We have seen that all these results hold without any sparsity constraint. So I can conclude, at least from a theoretical point of view, that sparsity is not the answer for the success of deep neural networks. And I would like to end up my talk with the following quote, which I really like. By far, the greatest danger for artificial intelligence is that people conclude too early that they understand it. I thank you for your attention.
Yeah, thank you so much for a great lecture. Are there questions? I saw already one question in the chat. So there was a question by Mehmet Kana, which is why truncation? What is the technical reason? I think it was right at the beginning of the talk.
Yeah, exactly. So you need this for bounding the covering number, for example. Yeah, that's the reason is in the proof. So it doesn't work for when the size can be infinity.
Okay, thank you. So the next question is targeted at slide 18-19, and it is by Franka Hoffmann. She's asking, I mean, do you make any use of the geometric structure of the manifold beyond the manifold dimension?
I'm not sure if I get it right, but
maybe Franka, you could also maybe demute yourself and clarify your question a bit.
Hi, hello. Yeah, it was just to ask if you look into more what is the distribution of the data on the manifold. From what I see from the result, what comes into the result is the dimension of the manifold, right? Yeah, so the question is if there's any other information about the manifold or the distribution on the data that you use.
No, I did not use any other distribution, only the dimension of the manifold.
I think that could be something interesting.
Yeah.
Thanks. It was a really, really wonderful talk.
Thank you.
Other questions? So maybe to your definition of function spaces, so there's also this notion of compositorial functions by Tommaso Poggio and Hrusikesh Mascar. Can you maybe say how this is related?
I'm not sure if I know the definition of these two, so
okay.
Sorry.
Yeah, no problem. I mean, might just be interesting to look to look in there.
So I have to check it out, and maybe then I can tell you.
Okay, so there's another question by Mehmet Kayna. He's asking, sparsity is introduced in input dimension and the cost is log n to the 6 power of 6 rather than log n to the power of 3.
I'm not sure if I'm not sure which log Schmidt-Hieber has in his results. I think it's a log 3, and yeah, that's true. So we have a higher log factor, but yeah, in this statistical analysis, this log factor is sometimes we do not look at the log factor. We only check the rate of convergence, but it's true. So we have a higher log factor in this result.
Okay, further questions at this point? Yeah, if not, then let's thank our speaker again.